We had already discussed about the principle of the galvanometer, that it is based on the principle of the torque that acts on a current carrying coil placed within a magnetic field, and the pointer arrangement in the galvanometer that is attached to the given coil, which experiences a certain deflection the upon the torque that acts on the galvanometer due to the passage of current within the permanent magnets that are placed, and also the case where the galvanometer was sensitive to the currents or the voltages that are developed across the circuit. Now, the resistance of the galvanometer and the current needed to produce a full scale deflection is very small. Now, the resistance of the galvanometer is typically of the order of 20 ohms, while galvanometer current that is of 1 milliampere is sufficient enough to produce the full scale deflection. Now, these are some of the things that inspire the galvanometer to be used uh, as ammeter as well as voltmeter, and as far as the conversion of a galvanometer into an ammeter is concerned, which is the first thing that we are going to take a look at. Now, the conversion of the galvanometer firstly to an ammeter involves the uh, involves connecting a low resistance shunt. Now, any resistance which is connected parallelly is typically called as the shunt, and that is connected, or the galvanometer is said to have been shunted, and this results in the galvanometer being converted to an ammeter. So here is supposedly the galvanometer with a resistance of G, and the circuit carries a certain current I, and which further gets divided as per the following the uh, junction rule. So here we have Ig to be flowing through the galvanometer, while the current devoid of Ig flows through the shunt resistance. So this is I minus Ig, which again adds up to the Ig to give back the current I. Now, this galvanometer can measure the current, as I said, of 1 milliampere. However, in practice, we have to measure large currents, and in that case, a suitably low resistance, that is the shunt resistance, which is S that I have indicated over there, that is connected in parallel to the galvanometer, and this arrangement, as I said, is constitutes or forms the ammeter. Now, what is the value of that shunt resistance, uh, which needs to be known in order to get the galvanometer to work on a given range or on a given scale? So in order to obtain the value of that resistance that we have shunted the galvanometer with, we simply consider the potential difference. If we have 2 points A and B over there, the potential difference across AB is going to be the same for parallel combination, as we know right from the very beginning. So in that case, we have the potential difference across AB to be equal to the current that is flowing across the galvanometer multiplied to the resistance of the galvanometer, and that must be equal to the potential difference that we observe across the shunt, which is the product of the current that is flowing with the resistance that is there. So that results in the shunt having the value Ig upon I minus Ig multiplied with a G. Now, as one can see over here, the value of Ig is comparatively less than that of I, and as a result of that, the value of shunt is very, very low. Now this connection of the shunt in parallel, of the resistance S in parallel with the galvanometer as per the given equation, results in an ammeter of the range of the ammeter is now from 0 to I amperes. And we replace the 0 to Ig range has been replaced by the scale of 0 to I, and that is what that is the arrangement that is made in case of the ammeter scaling, instead of that in case of the galvanometer scaling. The galvanometer scaling is in milliamperes. Even it's up to 1 milliampere, but in case we have converted that to an ammeter, we need to change the scale as per the range that we expect it to work within. Now this resistance of the ammeter that we get, that is a parallel combination of the shunted arrangement with the galvanometer. So the resistance of the ammeter as a whole is going to be the parallel combination of both those resistances, that is G and S. So that gives G times of S divided by G plus S. As quite clear, this resistance will be less than resistance of the ammeter is going to be less than that of the shunt resistance. So it's a very, very small value, and because this is low, this kind of arrangement, or this ammeter, does not really affect any value of in the flow of current, and as a result of that, this ammeter arrangement is connected in series to the given circuit where the current is to be obtained. It has to be connected in series, of course, because if we are going to connect it in parallel, then it will collect a part of the current from the circuit, and it won't really help. So it has to be connected in series to the circuit, and as a result of the low resistance of the ammeter, we do not experience any fluctuations, any marked fluctuations in the value of current. Now as we can see over here, the shunt has not only extended the current range, but it has also lowered the resistance of the ammeter. Now if there are n number of scale divisions, if there are n number of scale divisions in the galvanometer, then with K being the current for one scale deflection in the galvanometer, we have the full scale deflection current for the galvanometer to be equal to Ig, that is equal to N times of K. Now as far as the use of the shunt is concerned, the shunt is a low resistance which is connected in parallel, as we see. So the shunt is used to convert a galvanometer into an ammeter, and the shunt may be used to increase the range of the ammeter as well. While determining the null point in the meter bridge and the potentiometer experiments, a shunt is used to protect the galvanometer from damage due to excessive current. So that is one of the main uses of shunt while considering the case of meter bridge as well as the potentiometer. Up next, we are going to discuss about the conversion of the galvanometer into the voltmeter. Well, this is more or less the circuit of a galvanometer being converted to a voltmeter. Now, uh, as in case of the galvanometer considered solely, the full scale deflection that we see for the current in case of a galvanometer, as I mentioned, is just 1 milliampere, while the resistance of about 20 ohm is present in the galvanometer. The potential difference of supposedly a very less amount of 20 millivolt if applied across the galvanometer, then it will result in a full scale deflection, just like in the case of 1 milliampere being the current. Now this means that the galvanometer can read only up to 20 millivolts, but as far as the measurement of the potential difference is concerned, which is more or less the work that is required out of the voltmeter, what we do is we connect a suitable high resistance R. Now R here is known as the multiplier, and it is connected in series as opposed to the parallel connection of the shunt in case of ammeter. The multiplier, that is R, which has a very high value of resistance. So this shunt that I have shown over there, that is a very low resistance. That is very low resistance. While the case of multiplier, obviously as the name suggests, the resistance is very high. So the difference is quite a marked one in case of the galvanometer being converted to a voltmeter. Now, as far as the value of the voltmeter, the resistance in the voltmeter is concerned, we can calculate it in the following manner. Now, as this is connected in series, if we consider, again we consider 2 points over here, let us say this is A and this is B, and between those points A, B, as you can see, we have the voltage that has been applied by the circuit as V. This voltage is provided throughout the combination of resistance, which is carrying a current supposedly I. So I times of the total resistance in this case of series combination is going to be the sum of both those resistances, and finally what we are going to end up with is the value of R being equal to V divided by I. Now this I can, because it goes through the galvanometer, because this current goes through the galvanometer, we can just write it as Ig instead of I. So V divided by Ig minus G gives us the value for the resistance. And by connecting this high resistance in series with the galvanometer, we convert the voltage range from 0 to V volts. And because the resistance, as you can see, is pretty high, the total resistance in this case, the resistance of the voltmeter, that is going to be R plus G. And as we can see that the resistance of the voltmeter will be very high, it will be greater than that of the resistance, the multiplier resistance, because it has the factor G added to it. So the series resistance has not only extended the voltage range, but it has also increased the resistance of the voltmeter, and as a result of that, the voltmeter is connected in parallel to a given circuit, or between the points where the potential difference is to be obtained. Take for example the points that we have there, A, B, they are connected. So this entire, now let me mark these arrangements that we have just obtained. The green dotted lines that we see over there, the green dashed lines, not the dotted ones, but the green dashed lines that I have just drawn, they give the arrangement or the setup of the ammeter at the top and the voltmeter at the bottom. What we essentially do is that if we have a circuit, let us say, let me draw a circuit for you. So supposedly we have a circuit over here which has a certain potential source, and that is providing a voltage V, and we have a resistance R, and now we are to determine the current, and for that we are having the ammeter arrangement over here. So this is the, let's say this is the ammeter, and we wish to obtain the potential difference between the ends of the resistor, and as a result of that we attach a voltmeter. Now this voltmeter and this ammeter that we see over here is completely this setup, where this is the voltmeter, the dashed lines, and the dashed lines give the ammeter circuit at the top. What happens essentially over there is that as a current is established in the circuit and it flows, now with that voltmeter connected in parallel between those 2 points, let me mark those points with some other ink for you. So we have the red points over there which are parallel to the resistance over there and the voltmeter which is connected in parallel. Now what essentially happens over there is that the current that passes through that, the current cannot pass through the voltmeter. It will be completely negligible because the voltmeter has a very, or provides a very high resistance to the flow of current in that path, and as a result of that very feeble amount of current will be able to flow through that, which is, again, as I mentioned, it will be highly negligible because the multiplier resistance is maintained at very high value. But so the maximum amount of current, almost 99 or more than that percent of current, passes through the resistance, that is R, that has been provided in the circuit right from the very beginning. Now with that entire current being passed through that R, we get the entire potential difference that we wish to obtain between those 2 points, and that potential difference that we wish to obtain, that is reflected in the voltmeter which is connected in parallel, because it will be having the same potential difference. And as a result of that, what happens is that this voltmeter will give us the exact value of the voltage that is present in that circuit at that instant of time, and the pointer of the galvanometer, the pointer arrangement obviously, which is the principle of working of the galvanometer, is there in the voltmeter to provide us with the accurate deflection over the required, or over the exact value that we wish to obtain. And similar is the case with the ammeter, where the entire current passes through the ammeter, and it experiences the least potential drop, or least least amount of current is consumed, because the corresponding resistance of the ammeter is very low. So again, we have the maximum amount of current that is present, or that is collected between the ends of the ammeter, and as a result of that, that deflects, or that produces the necessary torque in the galvanometer, thereby allowing the deflection of the coil as well as the pointer attached to it, showing the accurate reading based on the range that we have provided. So that is more or less the case of how we use the galvanometer as to be converted in the form of ammeter as well as voltmeter. Now, having discussed the whole case of the galvanometer conversion, we can afford to try a few numericals, at least a few of them right here, so that we are clear with the way those things are working. So let's consider the first one over here. It says that a galvanometer has a coil of resistance 5 ohms and requires 15 milliampere for full scale deflection. So we have the G and the IG over here. So how can we convert it into the first case being an ammeter of the range 0 to 1 ampere, and the second case being voltmeter of the range 0 to 15 volts, and we are also to determine the resistance of the meter, the corresponding meter, that is ammeter or voltmeter in each case. So what we are supposed to do over here, what are the things that we have at hand? Let's see that first. So considering the solution over here, we seek the answer, and we have the value of G, as I said, is 5 ohms, and we have IG as well, and that is 15 milliamperes. So that's what has been provided to us. Also, what has been provided to us is that we seek to obtain in the first case the value of I from 0 to I scale, that is the range of the ammeter is 1 ampere in this case. So we wish to obtain the shunt resistance. Now the shunt resistance, as we know, is simply expressed as Ig divided by I minus Ig times of G, and that equates to the value of Ig being 15 milliampere. We take it in terms of ampere, and here we have 1 ampere minus the 0.015 milli or 0.015 amperes, which is 15 milliampere, multiplied to 5, that is the resistance of the galvanometer, and this approximately results to 0.076. correct me if I'm wrong, you can check for yourself. And then we wish to obtain the resistance. In this case, the resistance here being the case of ammeter arrangement, which has G times of S divided by G plus S. So that is 5 times of 0.076 that we have obtained for S, divided by 5.076, adding it directly, and this approximately gives, obviously it will be less than that we have for the resistance, shunt resistance, so it is less than the shunt resistance over here as well, as we can see, as quite evident in this case. Now as for the second case, where we wish to obtain the voltage or the resistance, the multiplier resistance first of all. So in the second case, we wish to obtain the multiplier resistance. Now the voltage, the multiplier resistance, that is equal to V divided by Ig minus G. Now we wish to convert it to a voltmeter of voltage ranging up to 15. So V is going to be 15. Ig, we have it is 0.015, and the value of G being equal to 5. So we have this value. This is 1000 times, and 1000 minus 5 is 995. So this is the resistance of the multiplier that we have provided in the galvanometer, the voltmeter circuit, to in the galvanometer circuit, to convert it into a voltmeter, of course. And then we seek the total resistance, that is R volts, suppose, is equal to R plus G, and guess what, it is coming to a very good number, which is 1000 ohms. So this is the value of the total resistance. Now I'm finding it pretty interesting. Let's try another one. So what does the second one say? It says that a galvanometer gives a full scale deflection or reading of 25 milliamperes when a potential difference across its terminals is 75 millivolts. So here we have the potential difference which results in that full-scale deflection. Remember in the previous, while considering the theory, I had mentioned that full-scale deflection of about 1 milliampere for 20 millivolts or something like that. And here we have it as 25 and 75, and how it can be used, and we wish to find the ammeter uh, in the range of 0 to 100 amperes and the voltmeter in the range of 0 to 750. That's quite large. So let's see what we have in store for us. We have the galvanometer resistance that we wish to find, because that's not given over here, because without that we cannot really have the aiding formula to obtain those shunt resistance and the multiplier resistance that we wish to find, because that is what we have to find in order to convert it to a certain given range. So we wish to obtain the galvanometer resistance, and now that will be equal to the voltage divided by the current. So the voltage over here is, so G is going to be equal to the voltage which is 75 millivolts divided by 25 milliampere. We need not write the units though, but still it's 3 ohms. The millis get cancelled out, and the volt by ampere is going to give me ohms. So now the full scale current, we know it. The full scale current that is possible in the galvanometer is given to be 25 milliamperes. That's for sure. And that's approximately 0.025, as in the previous case we had seen 0.015, 15 milliamperes. Now if we wish to obtain the shunt resistance for the ammeter of the range of 100 amperes, so first of all we would like to obtain take S, and for that S we have Ig times of G divided by I minus Ig, and that is going to be equal to 25 milli, which is 10 to the power minus 3. I keep it like that, and that of the galvanometer is 3. And here I have the value that is 100. We wish to take it to 100 minus, that is 0.025, and this will approximately give me the result to be equal to nearly 7.5 times of 10 raised to the power minus 4. Again, you can check this for yourself. This hasn't really asked us to obtain the net resistance, so we do away with that. And now we wish to obtain the multiplier resistance so as to be used in case of the voltmeter of the range of 750. So V by Ig minus G, which is over here, it is 750 divided by it is 25 times of 10 to the power minus 3, and the value of G as we know it is simply 3. Now this is it's 30 and 30,000 minus 3, which is 29,997 ohms, so quite a high value. So as you can see, the value of these shunt resistance and the multiplier resistance, they determine the range. In case the range was something different, we would have had some different value of shunt as well as the multiplier resistance accordingly. So that's more or less the thick and thin of it, and we have come to the end of the topic, that is magnetic effect of electric current. We'll be starting off with a new one in the next. We'll be doing a new playlist for that. Till then, thank you for watching.